Cams are used to create motion in various machines and devices. Complex cam systems can be found in car engines and oil pumps, while simpler versions can be found in children's toys. A cam is a mechanism that moves to change the direction or rhythm of movement of other parts. Usually cams are rotated by an axle or shaft and cause linear movement of another part or parts. A cam mechanism is made up of just a few parts: a crank, axle, cam, follower, and a guide. The crank turns the axle or shaft, which then rotates the cam. The follower rests on the cam's surface and moves through a guide as the rotating cam surface displaces it. The follower is converting the cam's rotational movement into linear movement. The cam's shape is referred to as its profile, and there are many different types of profiles. This is an example of an elliptical cam, but there are also circular, pear, eccentric, hexagonal, snail, and heart profiles. We can create a graphical model to represent the linear motion of the follower caused by the rotation of a cam with a motion graph, similar to the motion graphs we created earlier in this unit. In this motion graph, the height of the follower is graphed with respect to the angle of rotation of the cam. Remember that the motion graphs we created earlier included time as the independent variable. In this case, the angle of rotation is the independent variable. We can easily convert the independent variable to time if we know how fast the axle is rotating. Let's investigate how this motion graph relates to this cam. We adjust the cam so that the follower will be in its lowest position, which we'll call 0 degrees. We'll rotate the cam 45 degrees and mark the new position of the follower. We repeat this process of marking the position every 45 degrees until we reach 360 or 0 again. The resulting graph shows the motion of the follower over one complete rotation of the cam. In the cam assembly, the difference between the lowest and highest position is the amount of the vertical movement that the cam produces in the follower, also known as the maximum displacement of the follower. Another way that we could measure the vertical motion of the follower is the measurement from the center line of the axle to the top of the follower rod. We can create another motion graph related to the first using this measure of vertical motion. Let's compare the two motion graphs. They both display the same maximum displacement. One graph is higher on the grid than the other. In other words, the resulting motion is the same for each graph. The difference is that the motion represented by the blue graph started at a greater magnitude than the motion represented by the red graph. This tells us that the reference point, the point from which we measure the displacement, doesn't really matter. The maximum displacement remains the same. Also, it's important to note that the length of the follower doesn't affect the displacement caused by a cam. The length of the follower only determines the initial position, not the magnitude of the displacement. This difference in magnitude is consistent throughout, meaning it's the same difference at any angle of rotation. So what do you think this value represents? It's actually the vertical distance between the center line of the axle and the top of the box. This is an example of the motion of a pear-shaped cam. What would the motion graph produced by a round cam look like? A hexagon cam? A snail cam? You will have the opportunity to explore and learn about the motion produced by a variety of cams in the next activity. As you learn about the motion produced by cams, think about the motion that you would like to replicate in your automata design. What shape of cam will best replicate the desired motion?